In the world of LLM serving, the most terrifying sound isn't a bug report, it's the silence of a dead GPU after a QA out-of-memory error at 3 a.m. Many teams think that if a model fits in VRAM during a single user test, it's production ready. But in reality, once the traffic hits and concurrent requests scale, the overhead of the KV cache and activation buffers explodes. I've seen countless projects hit a wall because they treated GPU memory like a traditional RAM buffer. In production, LLMs consume resources in a non-linear fashion. You might have an 80 GB A100, but if you're serving a Llama 370B model in FP16, you're already at the edge before a single user even types a prompt. This invisible tax is what kills your budget and your reliability. This lecture isn't about theoretical math, it's about the engineering required to survive these spikes and keep your unit economics sustainable. By the end of this session, you will understand the exact mechanics of why these crashes happen and how to prevent them while cutting your cloud bill significantly. Let's start by looking at what we are actually aiming to achieve through optimization. Payoff beyond just stability. This optimization is what separates a profitable AI product from a money-burning experiment. Optimization isn't just a nice-to-have, it's a fundamental business requirement. When we talk about optimizing LLM inference, we're targeting 3 specific metrics: throughput, latency, and cost per token. In practice, most naive deployments are incredibly wasteful, often utilizing less than 20% of the theoretical GPU compute power because they are bottlenecked by memory bandwidth. Our goal in this guide is to move from a basic Hugging Face transformers setup to a high-performance serving stack using vLLM and advanced quantization like FP8 and ABQ. We aren't just trying to make it faster, we are trying to pack more requests into the same hardware. If you can double your throughput, you effectively cut your infrastructure cost by 50%. This is the difference between a project being greenlit or canceled by the CFO. We will follow a rigorous path, first identifying the bottleneck, then applying weight compression, and finally optimizing the serving engine's memory management. But before we touch any code, we must understand the physical constraints of the hardware we are fighting against. Question: why does a GPU with massive teraflops performance still struggle to generate text quickly? The answer lies in the memory wall. To master LLM serving, you have to understand the 3 pillars of pain: memory capacity, memory bandwidth, and compute throughput. Most people assume LLM inference is compute-bound, meaning the GPU cores are working at max capacity. In reality, LLM inference is almost always memory-bound. Think of the GPU as a high-speed factory where the workers, TUDA cores, are incredibly fast, but the conveyor belt, memory bandwidth, bringing them materials is too slow. Every time the model generates a single token, it has to read every single weight from VRAM into the on-chip cache. This is the memory wall. If your model is 140 GB in FP16 and your GPU only has 2 GB as bandwidth, you are physically capped on how fast you can generate text, regardless of how many teraflops your GPU has. Quantization isn't just about fitting a big model into a small GPU, it's about making that conveyor belt more efficient by making the materials smaller. Question: if weights are the problem, why does the memory usage keep climbing as more users join? That brings us to the internal breakdown of VRAM. Where does the VRAM actually go? It's not just the weights. In a typical production setup, memory is split into 3 main buckets. First, the model weights. These are static. For a 70B model in FP16, this is a fixed 140 GB. Second, the activations, the intermediate calculations during a forward pass. These are usually small but spike during processing. Finally, the silent killer, the KV cache. To avoid recalculating the entire sequence for every new token, we store the keys and values of previous tokens. This cache grows linearly with context length and batch size. In a high concurrency environment, the KV cache can actually exceed the size of the model weights themselves. This is why a model that seems fine during testing crashes when you increase the max context length from 512 to 4096. Understanding this distribution is key to choosing between ANT8 ABQ or FP8 quantization strategies. Teaser now we know where the memory goes. Let's look at our first weapon to shrink these weights without destroying the model's intelligence: the deep dive into quantization algorithms. In the field, we often hit the out-of-memory wall sooner than expected. Everyone talks about ANT8 being half the size of FP16, but by 2026, it is not that simple. Standard FP16 was our baseline, but keeping a 70B or 400B model in FP16 requires a massive VRAM footprint that destroys your margins. ANT8 quantization was the first industry savior, mapping 16-bit values to 8-bit integers, effectively halving memory usage. However, the rounding error in ANT8 often kills the nuances in high-reasoning models. This is where FP8 changes the game. Unlike ANT8, FP8 keeps a floating point structure with an exponent, preserving dynamic range while matching the speed of integer math. If you are still deploying 16-bit models on H100s, you are burning cache for precision that the user likely won't even notice. But wait, if we just shrink everything blindly, why does the model suddenly start hallucinating more? Question: this happens because some weights are far more important than others, a problem we will solve in the next scene. When we look at LLM weights, they aren't distributed evenly. Most weights are small, but a few outliers carry the vast majority of the signal. If you apply simple int8 quantization, these outliers get clipped or skewed, and your model's logic breaks. This is why techniques like GPTQ and AWQ activation-aware weight quantization are non-negotiable for 2026 production. AWQ specifically identifies the top 1% of weights that are most important for the model's activations and keeps them at higher precision or scales them carefully. In my experience, applying AWQ to a Llama 3 70B model allows it to fit on a single A100 while maintaining 99% of the original FP16 accuracy. Without these techniques, your quantized model is just a lobotomized version of the original. But does the software trick work on every GPU? Question: the answer lies in the silicon itself, which brings us to the latest hardware shift. In the 2026 landscape, the hardware-software marriage is tighter than ever. While AWQ and GPTQ were brilliant software hacks for older GPUs, the Blackwell and Hopper architectures have redefined the baseline. NVIDIA's H100 and B200 introduced native FP8 Tensor Core support, which means you get the best of both worlds: 8-bit memory savings and massive throughput without the complex calibration overhead of 4-bit INT quantization. For many enterprise teams, FP8 is now the Goldilocks zone. It is fast, hardware accelerated, and incredibly stable. If you are using L440S or H100 nodes, FP8 is your default choice for production serving. However, if you're forced to use older hardware like the A100 or cheaper consumer-grade cards, you'll still be relying heavily on 4-bit AWQ to survive. Payoff. Up until now, we have talked about the how, but how do we prove it actually works? The real disaster happens when you deploy without a validation strategy. Selecting a quantization method is not just a set and forget task. You need a validation workflow. In many projects, I see teams check perplexity and call it a day. But low perplexity doesn't mean your RAG pipeline won't break. You must follow a rigorous process. First, quantize with a tool like AutoAWQ or TensorRT-LLM, then run a standard benchmark like MMLU, and finally, test on your specific domain data. If your model is supposed to write Python code, but you only validated it on general English text, you are in for a surprise. I've seen 4-bit models pass general benchmarks but fail miserably at syntax. Use a small, high-quality evaluation set that reflects your actual user prompts. This validation step is what separates a professional deployment from a hobbyist experiment. Question: but where does this validation data come from? If you use the wrong calibration set, the whole house of cards falls down. The calibration set is the most misunderstood part of quantization. When techniques like AWQ or GPTQ run, they need a small sample of data to observe how activations flow through the model. Many people just use Wikitext or some random data set from Hugging Face. That is an anti-pattern. If you are building a medical LLM, calibrating on Wikipedia will make the quantization process ignore the weight ranges critical for medical terminology. You only need about 128 to 512 high-quality samples. These samples should mimic the distribution of your real-world traffic. This ensures that the clipping and scaling factors are optimized for what your users actually type. Payoff. Until now, we've looked at the technical steps. Now, let's look at the actual decision matrix you'll use in your next meeting to choose the right format. To wrap up this chapter, let's look at the decision matrix. If you have A200 or B200 GPUs, FP8 is your winner for 90% of use cases. It offers near zero accuracy loss and is natively supported by engines like vLLM and TensorRT-LLM. If you are on older A100s or L4s and need to fit a huge model like Llama 3 70B into a single card, 4-bit AWQ is your only choice. It's slower than FP8 due to the dequantization overhead on every forward pass, but it saves your budget from buying 3 more GPUs. Never use basic NT8 unless your specific hardware lacks FP8 and your serving engine doesn't support AWQ. This decision directly dictates your tokens per second and your cost per 1K tokens. Teaser, but even the best quantization won't save you if your serving engine is inefficient. In the next chapter, we'll see how vLLM takes these quantized weights and turns them into a high-speed inference factory using page detention. In the real world, your LLM serving dies not because the model is too big, but because your GPU memory is fragmented. You've probably seen your server crash with an out-of-memory error, even when there should be enough VRAM left. This happens because traditional inference engines allocate contiguous blocks of memory for the KV cache based on the maximum sequence length. If a user only asks a short question, that reserved space is wasted. vLLM solves this using page attention, which is inspired by the virtual memory management in operating systems. Instead of one big block, it breaks the KV cache into small, non-contiguous physical blocks. This allows the engine to utilize almost 100% of the KV cache memory, which means you can pack more requests into the same hardware. It's the difference between a half-empty parking lot and a perfectly optimized automated garage. But managing memory is only half the battle. We still have to figure out how to keep the GPU cores busy. Actually, do you know how much idle time your GPU currently has while waiting for sequences to finish? Next, I will show you how to eliminate those wasted cycles entirely. In standard static batching, the GPU is a slave to the longest sequence in the batch. If one request generates 500 tokens and another only 10, the second request just sits there wasting expensive GPU cycles until the first one is done. This is a budget killer for high-traffic services. vLLM implements continuous batching, which operates at the iteration level rather than the request level. As soon as one request finishes, a new one is inserted into the running batch without waiting for others. This keeps the GPU compute unit saturated and maximizes your requests per second. When you look at your monitoring dashboard, you'll see throughput numbers double or triple simply by switching from static to continuous batching. It sounds like a silver bullet, right? However, there is a catch. As you add more concurrent users, the complexity of managing these overlapping KV caches grows exponentially. Let's look at how the engine actually tiles these caches to prevent the whole system from slowing down under pressure. As we scale to hundreds of concurrent users, the KV cache becomes a massive multidimensional puzzle. vLLM handles this through KV cache tiling and efficient block management. Each user's context is broken into blocks, and these blocks are shared and mapped across the GPU memory space. This is crucial for techniques like parallel sampling or beam search where multiple outputs share the same prefix. Instead of duplicating the memory for that shared prefix, vLLM just points multiple logical blocks to the same physical page. This is where the true cost savings happen in production. If you are serving a chatbot that uses a long system prompt, you aren't paying for that prompt 100 times, you're paying for it once. But here is where it gets tricky. What happens when we combine this complex memory management with the quantization techniques we discussed earlier? If the engine doesn't understand the quantized format at a low level, all these speed gains will be wiped out by decoding overhead. I'm going to show you exactly how to bridge that gap in the next section. A common mistake I see is engineers thinking that simply quantizing a model is enough. They load a 4-bit model into a basic engine and wonder why the throughput hasn't improved. The reality is that for quantization to actually save you money, the serving engine must have specialized kernels that can read those specific memory layouts without constant dequantization back to FP32. vLLM is specifically optimized for this. When you use a format like ADQ or FP8, vLLM uses custom QDA kernels that perform the math directly on the smaller data types or use highly efficient weight-only unpacking. This memory alignment is the secret sauce. If the data isn't aligned with the GPU's memory bus width, you'll suffer from bank conflicts and slow performance. So before you commit to a quantization strategy, you must ensure your engine vLLM, and in this case, fully supports that specific format's layout. Now, you might be asking, how do I actually set this up without breaking my head over QDA code? The good news is that it's usually just a single line in your configuration. Let's look at the actual commands you need to run. Setting up vLLM for quantized serving is surprisingly straightforward, but if you miss the specific flags, you'll end up running the model in full precision and running out of VRAM. For AWQ, which is excellent for 4-bit weight-only quantization, you simply use the quantization awk flag. For the newer FP8 format, which offers a better balance between speed and accuracy on A200 or A100 GPUs, you use quantization FP8. You also need to pay attention to the type flag. Setting it to auto or half is usually the safest bet for older hardware, while bfloat 16 is preferred for modern cards. I've seen teams struggle for days only to realize they were loading a quantized model without the correct flag, causing vLLM to try and upcast everything to FP16, which then crashes the GPU. These CLI arguments are your primary leverage for controlling the serving cost. But what happens when even a quantized model is too big for a single GPU? That's where distributed serving comes into play, and vLLM makes scaling surprisingly easy. When you're dealing with massive models like Llama 370B, even with quantization, you'll need multiple GPUs. vLLM supports tensor parallelism, TP, and pipeline parallelism, PP, out of the box. Tensor parallelism splits individual layers across multiple GPUs, meaning they all work on the same layer at the same time to reduce latency. This is almost always what you want for real-time inference. vLLM uses Ray or its own custom distributed stack to handle the communication between these cards. The beauty is that the paged attention we talked about earlier still works across these distributed setups. However, be warned, the communication overhead between GPUs can eat up your performance gains if your NVLink or PCI bandwidth is slow. It's a delicate balance between the model size, the quantization level, and the number of GPUs. We've covered the math and the engine mechanics, but the real world is messy. In the next chapter, we're going to dive into war stories, actual bottlenecks we've encountered in production that no benchmark will ever tell you about. In the field, we often see teams jumping straight into 4-bit quantization because the memory savings look incredible on paper. But here is the cold reality. I've seen advanced reasoning models completely lose their ability to perform basic arithmetic or follow nested logical constraints immediately after a naive 4-bit AWQ conversion. It is not just a slight drop in accuracy, it's a structural regression. While the model might still sound fluent, its internal world model can shatter. This happens because certain outlier weights, those high-magnitude values critical for logical precision, get crushed by the quantization grid. If your application involves financial calculations or legal reasoning, you cannot just trust the compressed weights without rigorous unit testing for logic. In one project, we found that moving from 4-bit back to 8-bit or FP8 was the only way to recover the required accuracy, even if it meant higher infrastructure costs. Don't let the allure of half the VRAM blind you to the fact that a fast, cheap model that gives wrong answers is worse than no model at all. But why does this performance vary so wildly across different hardware setups? Let's talk about the hardware trap. You finally get your quantized weights ready. You fire up vLLM, and the speed is exactly the same as the uncompressed model. Or worse, it's slower. This is the environment trap that catches many engineers off guard. Quantization isn't magic. It relies on highly specialized GPU kernels like AutoEQ or Marlin to handle the bit-shifting maths. If your QDA toolkit version, NVIDIA driver, or even your PyTorch build doesn't perfectly align with the serving engine's requirements, the system might fall back to generic kernels that are unoptimized. Furthermore, older architectures like the T4 or even the A10 don't support the latest FP8 or optimized INT8 instructions that newer H100s do. I have seen countless hours wasted troubleshooting slow inference only to find the team was running a version of vLLM that didn't yet support the specific quantization kernel for their GPU architecture. You must verify the compatibility matrix of your hardware, driver, and serving engine before committing to a quantization strategy. And even when everything is compatible, your performance might actually drop as you scale down. Here is why. This is one of the most counterintuitive traps in LLM serving. Quantization can actually make small models slower. If you are serving a 1B or 3B parameter model, the bottleneck is often not memory bandwidth, but the overhead of launching the kernels themselves. Every time a layer is processed, the GPU has to load the quantization parameters and dequantize the weights in real time. For a massive 70B model, this overhead is negligible compared to the massive memory savings. But for a tiny model, the time spent on kernel launch overhead can be greater than the time saved by reading fewer bits from memory. In the field, we call this being compute bound vs IO bound. If your model is small enough to fit comfortably in FP16, adding quantization might just add latency without any throughput gain. I've seen teams over-engineer their stacks with complex AW pipelines for small models, only to find that raw FP16 was faster and more accurate. So if the model size isn't the only variable, how do we actually measure what's happening under the hood? Time to talk metrics. When you're monitoring a production LLM, don't just look at tokens per second. That is a vanity metric that hides the real user experience. In the real world, you must track two critical numbers: time to first token, TTFT, and time per output token, TPOT. TTFT is what makes a user feel the system is fast. It's the latency from clicking send to seeing the first character. If your TTFT is over 2 seconds, your UI will feel sluggish regardless of how fast the rest of the sentence generates. On the other hand, TPO determines the writing speed. If it's too slow, the text crawls. If it's inconsistent, jitter, it's annoying to read. In optimized serving like vLLM, we also look at inter-token latency. When you quantize or change batch sizes, these metrics move in opposite directions. Increasing batch size helps throughput but often hurts TTFT. Understanding this trade-off is the difference between a system that looks good in a report and one that feels good to a user. Now that we know what to measure, how do we break our system before our customers do? Real-world traffic isn't a single prompt in a clean script. It's 100 people asking long context questions at the same time. To simulate this, you shouldn't build your own load tester from scratch. vLLM provides a robust benchmark serving script in its source code. I highly recommend using it. It allows you to simulate Poisson distributions of requests, which mimics how real humans actually interact with an API. You can feed it a dataset like ShareGPT to see how your quantized model handles varying prompt lengths. If you only test with short 10-token prompts, you'll be shocked when your KV cache overflows in production because your users are pasting 2,000-word documents. Running these benchmarks reveals the saturation point, the exact moment where adding one more user causes the latency to skyrocket. Find that point before your users do. But performance is only half the battle. At the end of the day, someone has to pay the bill. Let's talk about the bottom line, TCO, or total cost of ownership. Many developers think that expensive GPU equals expensive service, but the math often says the opposite. For instance, an H100 might cost 3 times as much per hour as an A100, but if its FP8 support and memory bandwidth allow for 5 times the throughput, your cost per 1 million tokens actually drops significantly. Optimization is what enables this leverage. By combining AWQ quantization with vLLM's paged attention, you can fit larger batches and larger models onto fewer or cheaper GPUs. In one scenario, we moved from 4 nodes of A100s running FP16 to a single node of A200s running FP8, reducing the monthly bill by 40% while doubling the capacity. This is the decision frame you need to bring to management. Don't just ask for a GPU, show them the tokens per dollar improvement. We've covered the war stories and the math, but how do we turn this into a standard operating procedure? That's what we tackle in the final chapter: best practices and future proofing. In the early days, we just used post-training quantization because it was fast and easy. But in the 2026 landscape, as we push for 4-bit or even 2-bit deployments on the edge, the accuracy drop in PTQ becomes a deal breaker for production. This is where quantization-aware training, or QAT, becomes your secret weapon. By simulating quantization noise during a short fine-tuning phase, the model learns to compensate for the lost precision. In my experience, if you're dealing with complex reasoning tasks or high-stakes financial data, PTQ might lose 5% accuracy while QAT keeps it within 0.5%. It requires more compute upfront, but when you're scaling to millions of users, that tiny bit of extra training is peanuts compared to the inference savings you gain from running a smaller, quantized model. Don't just compress with intelligence. But wait, compression is only half the battle when it comes to raw tokens per second throughput. Question, is there a way to cheat the sequential nature of LLMs? We're about to look at a method that literally guesses the future. If you want to see a 3x jump in speed without buying a single extra H100, you need to understand speculative decoding. Here's the deal. We use a tiny, ultra-fast draft model, think a quantized 1B or 3B model, to predict the next few tokens in parallel. Then our massive 70B target model verifies those guesses in a single forward pass. Because modern GPUs are often bottlenecked by memory bandwidth rather than compute for small batches, verifying 5 tokens takes almost the same time as generating 1. When you combine a quantized draft model with an FP8 target model in a vLLM environment, the performance gains are staggering. I've seen teams reduce latency from 100 ms per token down to 35 ms just by implementing this correctly. It feels like magic, but it's actually just efficient hardware utilization. Payoff, this sounds like the ultimate solution, but as a senior engineer, I've seen people burn their budgets by applying these tools to the wrong problems. Let's look at the hard do's and don'ts. In the real world, optimization is a double-edged sword. Don't quantize your model to 4-bit just because it's the trend. If your users are doing complex Python code generation, the logic will break. Do start with FP8 if you're on Blackwell or Hopper GPUs. It's the safest free lunch in 2026. Don't forget that your KV cache is often the real memory hog, not just the model weights. If you optimize weights but ignore paget attention or KV cache quantization, you'll still hit an error when your context window grows. I always tell my juniors, measure the cost per token and perplexity simultaneously. If cost goes down but perplexity spikes, you haven't optimized, you've just broken your product. Keep these rules in your pocket before you touch a single line of config. Teaser, now that you have the technical checklist, let's talk about the actual migration strategy. How do you move a live service without a 2 a.m. emergency call? Moving a legacy inference service to a modern quantized stack is like changing the engine of a plane while it's flying. You start with phase 1, establish a baseline using your current FP16 setup. Without metrics, you're just guessing. Phase 2, create your quantization profile using Audio ADWQ or TensorT LLM on a representative golden dataset, not just random text. Phase 3 is critical, traffic shadowing. Send a copy of production traffic to your new quantized vLLM instance and compare the outputs. If the semantic similarity is above 0.988 and your latency is 50% lower, you're ready for phase 4, the canary rollout. Never, and I mean never, flip the switch for 100% of users at once. I've seen the most optimized models fail on edge cases that weren't in the test set. Question, but what specific tools should you actually install to build this pipeline? Let's look at the 2026 standard stack. To survive as an AI engineer in 2026, your tech stack needs to be modular. At the bottom, you need a quantization toolkit like AutoAWQ or Quark to prepare the weights. Then, you need an inference engine. vLLM is the current king because of its paget attention and FP8 support, but keep an eye on SGLang for even faster scheduling. For the orchestration layer, use something like Kubernetes with Kubre to manage GPU clusters. And finally, the most ignored part, observability. If you aren't tracking GPU cache utilization and requests per second per dollar in Prometheus and Grafana, you aren't doing senior level work. This stack isn't just about making things work, it's about making things profitable. When your CFO asks why the GPU bill drill dropped by 40% despite traffic doubling, you'll point to this stack. Payoff, we've covered the how and the what, but let's finish with the why, the mindset that separates a coder from a senior engineer. Listen, the AI hype is everywhere, but the real winners aren't the ones with the biggest models, they're the ones who can serve those models the most efficiently. In my decades of experience, infrastructure efficiency is the ultimate competitive advantage. Any startup can burn $1 million on H100s. A senior engineer, however, can provide the same value for 200,000. That difference is your value to the company. Quantization, FP8, and vLLM aren't just technical buzzwords. They are the tools of fiscal responsibility in the age of AI. Take these lessons, go back to your teams, and look at your serving costs. Don't be afraid to break things in the dev environment to find that extra 20% efficiency. That's how you future-proof your career and your product. This concludes our series on the LLM serving trap. Now go out there and build something that doesn't kill your budget. Teaser, you've mastered the serving layer. Next time, we'll dive into the world of agentic rage where efficiency meets complex multi-step reasoning.